Welcome to the next video in the systems programming series. We're in chapter 2, moving on to section 2.4, and we're now going to talk about dynamic memory allocation. So you can read a bit of a general description of this, but let's skip down to malloc and free. The basic idea of malloc is that it will basically, determine a size. So I like to point to, actual uses of the object. That seems clear to me. So let's say that we have a variable p that is going to point to an address that holds an integer. And there are many reasons why we would want to allocate a necessary amount of size. So, what we've seen up to now is that we could declare some integer and put a value in there and then use the variable to get its address and put it into P. Well, what if we didn't want to do that, right? What if we wanted to simply get this pointer to some address in memory and simply give it some address, right? Put it somewhere. And we don't necessarily want to go through this other variable, right? For whatever reason, we may not feel that that is necessary for our purposes. So anyway, this is how you do it. But, if you're going to store an integer, then the compiler needs to know how much space it needs to go to reserve for this address, basically. So, when you declare a pointer, right, P is over here, and you want it to point to some location over here, the compiler needs to know how big this space is so that when you come around to putting an integer in there, it has enough space to hold an integer, basically. So that's the idea. And so this is why we need that sizeof function. It's so that we can figure out easily how much space we need. So if you say size of int, the compiler will know how much that is, and when you pass that into malloc, it will allocate the appropriate amount of space. Not only does it do that, but it also returns the address. So when you say p equals this, the address of that space is given over to p at the same time as it reserves the necessary amount of space. So that's the malloc function. What is worth knowing in this diagram is that every time you call malloc, malloc goes in what is called the heap. I'm not sure I know of a better way to describe what the heap is, except that it's the place where all dynamically allocated memory is held. So, okay. By the way, every time that you call malloc, it is good practice to test to make sure that the malloc was successful. There are some reasons why it can sometimes fail. And so, if you do a pattern like this where you check to see whether, right, if the malloc is unsuccessful, then what it will do is give P null. So the way that you test for whether malloc was successful is you test for whether or not P is null after performing the malloc. So this is a good, safe practice to make sure that you are referencing something that is really there. It is possible, right, because, so malloc technically returns something that is of type void star, and void star is basically just sort of the whole point of that is to be non-committal, right? Because several different kinds of data might hold the same size. So when you call malloc size of int, the compiler does not, right from that, know that what you're putting there is an int. It doesn't type it as an int. So it types it as void star, being basically agnostic as to what type of thing is going to be there. It just knows the size that it needed to reserve. Now, we know, and in fact, because of a line like that, the compiler knows that what is going to go here is an int, right? Because, we declared that P was a pointer to an int, and then we take the result of malloc and put it into P. So that is enough for the compiler to figure out that this, address is going to store an integer. Still, it is possible if you wanted to. I'm honestly not sure why you would want to, but you can cast that to an int star. So if it's returning a void star, you can put this cast and make it into an int star before assigning it to p. Since the compiler figures this all out anyway, I'm honestly not sure why you would choose to do that, but there's no harm in doing that. So okay, anyway. So here's some more testing for null, right? So declare your pointer, malloc, and int, and then check if it's null. This is actually a more common pattern, and this is where you start to see where a main function which normally returns 0 can return other things. And when you return other things, we often write it as exit. So exit 1 is effectively, as far as I know, it's effectively the same thing as return 1, but we often use it when basically returning an error message. But anyway, so if it is null, you usually like to broadcast to, say, the console or something like that, an error message and then exit the program. But if it was not null, then you'd like to continue with the program. This is a very typical design pattern. I'll be using it when I solve exercises and so on. So anyway, okay. Now that we're starting to get into reserving space in the heap, it is worth knowing that every time you malloc anything, if you are going to, sort of put something into the heap, you should always free it up at the end. So if you malloc p, which we did in this example up above, then by the time you're done using it, you should free p. Otherwise, you can get into some hard to sort of catch errors, and we'll look more at that later on. But the best thing to do is if you malloc anything, make sure by the end of the program you freed it. And it is good practice to also null any pointer once you're done using it. Now, we talked in a previous video about statically allocated arrays. So that would be something like int r bracket, we could say, right? So this would declare the variable r as an integer array, and to make it truly static, I would want to maybe say that it has 10 elements or whatever my choice was. But that's a statically declared array. It is not easy to change these choices, right? That it's going to be an integer array and store 10 objects. It's not easy to change your mind after you have made that choice. But here we're going to talk about dynamically allocated arrays where, basically because you malloc these things, that means you have the power to free them, as we've already talked about. Well, the fact that you can malloc them and then free them means that that's kind of like enough power to change your mind about the various decisions if you want to later on. So that's, I think, the main difference between statically allocated arrays and dynamically allocated arrays. So let's see how you do it, right? So if you have an integer array, then actually it turns out that the way that you can make a dynamically allocated integer array is with the exact same type as just a pointer to an int. The only thing that makes this a dynamically allocated array as opposed to just a pointer to an int is when we call malloc. So malloc down here, we give it the size of 20 integers. So that is the thing that makes this have the capacity of a 20 integer array, essentially. What this all kind of means, though, is that when you do this, the variable r here holds the address in the heap of this allocated space, and it points to the head of the space. So basically, when you call, or right when you follow this address, you are by default reaching the initial element of your array. It's pointing to the first element, or the address of the first element in the array. So, okay. And by the way, of course, right, we're talking about this with ints, but you could just as well do it with chars. Oh yeah, this is worth pointing out. When you malloc something, it gets you a contiguous space in memory. And in fact, we will exploit that. I mean, effectively what you can do, because you know that this is contiguous, is you can take this address, whatever this address is. If you add to this address the size of an integer, it will take you to the next address. That's a useful thing. We will use that sometimes. So whatever this address is, if you add to it the size of an int, it takes you to the next address. And likewise here, if you go, right, if you're talking about the address of 0 and you add the size of a char, it will take you to the next element of the array. So, this is all because when you malloc something, it gives you a contiguous space in memory. So the sort of contiguousness is, it allows for you to sort of simply add to the address and know that what you find there is going to be the next element in the array. If you add the right amount, it has to be the size of the thing that array stores. But what is important is that if you call malloc twice, right? So you call malloc for R, and then you also call malloc for CR, these two, addresses in memory are not guaranteed to be contiguous, right? So just because you called this and then immediately called this, that is no guarantee, and in fact it is almost certainly not true, that these two arrays, when it allocates them in space, will be contiguous. They almost certainly, they certainly will not be contiguous. So you can't, right, so like just basically what this is warning you against is thinking that you could add one to this thing and expect that the second array is located right there, right after the end of the first array. That is not guaranteed to be true. Let's see an example. So we declare an integer. What do? We make a static array. That's a static array with 20 elements. We make an int star d array. So as of now, right, except for the name of the variable, we could have thought that this was just a pointer to an integer. But then we would know that's not true when we come down here and see that we malloc size of int times 20. So that's a 20 element integer array, basically, dynamically allocated. We check to see whether it is null. That's always good practice. And then we perform a for loop. Now, you might be wondering, well, when you have a static array, we know what the syntax is for such things. Is the syntax for a dynamically allocated array any different? Like, say, when it comes to assigning the, doing coordinate assignment, right? So give me index I and I assign some value there. Is the syntax any different from when you do it with a statically allocated array? And the answer is no. So both with accessing, like doing coordinate assignment like here, or when you're simply fetching the value at some index in a dynamically allocated array, the syntax is exactly the same. So you can see that here, right? The syntax for getting the third coordinate of a statically allocated array is exactly the same syntax as getting the third coordinate from a dynamically allocated array. So, long story short, when it comes to basically using these things, like, getting values out of them or putting values into them, the syntax for static and dynamic arrays is no different. Now, one thing that is also a consequence of the fact that, this thing is basically pointing to the first element in a space reserved for the array, is that if you dereference, right, if you write star r. Now, normally, what does that do, right? We already know that when it comes to just a regular pointer variable, that is dereferencing. Therefore, it means that we follow the address to the value it is pointing to. If we apply the same logic when this is pointing to an dynamically allocated array, well, a dynamically allocated array is still pointing to the base address, the address of the first element. So even in this case, if you call star r, if you dereference r, what it will do is, follow the address and get the 0th element of the array. So hopefully, by having made that point, then this becomes clear. Using that familiar syntax of writing bracket 0 to get the 0th element is actually equivalent to calling star d array, blah, blah, blah. So anyway, okay, so I think I've made my point. So these two are equivalent to each other. Okay, but as always, because r was assigned basically by a malloc, then you want to make sure that by the time you're done using it, you free that memory. And because r is a pointer, then when you're done using the pointer, it's always good practice to null the pointer at the end. Same thing with cr, both freeing it and nulling the pointer, and so on. Okay, so now let's talk about passing these things into functions. So here the conversation is very similar to what we saw for statically allocated arrays, because after all, we kind of said that when it came to statically allocated arrays, when you pass them as arguments into a function, what you're really passing is the address. Well, here it's only just makes more sense because what this just is a pointer, right? Is an address to some location in memory. So of course that's just what is right. Like so when you when you have a variable that is being used to hold an array, right? So when you dynamically allocate an array, and then you pass that into some function, then the type that makes the most sense to use is exactly the type that was declared for the variable. It remains true that you want to keep track of the size, right? There's no reason, right? Like between what we talked about with static arrays and dynamic arrays, there's no reason why that would be any different. So you still want to pass in the size of the array, and then you use the array as normal. I guess perhaps it is worth noting, maybe it's worth noting, but in any case, that when you pass this into the function call, you simply pass the variable r1 here, rather than star or and or whatever. So, okay, anyway. It probably is worth pointing out, although, the same thing was said already for statically allocated arrays. It's still going to be true for dynamically allocated arrays. When you pass it into a function, because the pointer is the thing that is passed in, then whatever the function may do to the data at that address, those changes will show up in the main function, right? The changes are not constrained to the context of the function. They show up even when the function call is over, just as we have talked many times about other similar situations. So all the same stuff applies here.